This is section 5.2 on graphing polynomial functions. I'm just going to go ahead and cross off the objective for building cubic models from data. We're only going to focus on graphing a polynomial function. We are not going to focus on the building cubic models from data. All right, so let's go ahead with the steps for graphing a polynomial function. Actually, before we do that, let's start with talking about the steps. Step 1, determine the end behavior of the graph of the function. For end behaviors, I always think there's kind of 4 different instances that can occur. We could have something that looks like y is equal to x raised to an odd power. Or we could have something that looks like y is equal to a negative x raised to an odd power, which is going to look something like this. So notice that for the positive one, it's going kind of upward. For the negative one, it's going downward. And the reason I draw that squiggle in the middle part is because we really don't know what's going on in the middle. We don't know about, yet the x-intercepts or how many turning points. If we have y equal to x to the even power, it's going to go upward like this on both sides. And if we have y equal to negative x raised to the even power, then we're going to have something going downward like this on both sides. But once again, I draw the squiggle in the middle because we don't know what's going on in the middle part. All right. For these other steps, we did step 1. Step 2, find the x and y intercepts of the graph of the function. You guys know how to do that. Step 3, determine the real zeros of the function and their multiplicity and use this information to determine whether the graph crosses or touches the x-axis at each x-intercept. You know how to do that. We did that in 5.1. Step 4, determine the maximum number of turning points of the graph of the function. We did that in 5.1. You guys know how to do that. And step 5, use the information in steps 1 through 4 to draw a complete graph of the function to help establish the y-axis scale. Find additional points on the graph on each side of any x-intercept. We can do that, yes. All right, so here's our function. I'm going to start off by finding the degree of the function. So notice inside the parentheses, these x's are both raised to the first power. So that means I can just focus on the powers that are on the outside. So I'm going to focus on the one that's on the outside and the 3 that's on the outside. So those powers that are on the outside, I'm going to add those together. That's going to give me a 4. So that's going to tell me that ultimately if I were to multiply all of this out, I would end up with something like x to the 4th power for my leading term, or the degree of this polynomial function. I also have this negative 1/2 in the front that tells me a little bit about the end behavior, right? So I know that this polynomial function is going to look similar to y equal to negative 1/2 x to the 4th. If I had to explain to someone, what would it look like? So these are some important aspects of it. It's going to look something like this. I don't really know maybe what's going on in the middle there part, but I might definitely know for sure it's going to go open downward, and they're both going to go down on both sides. Okay, x-intercepts. To find x-intercepts, I would basically set my y equal to 0 and solve for x. So I'm just going to basically take the factors in here and I'm going to set them equal to 0 and solve for x. One of these is going to be x equal to negative 4. That's one of my zeros. Now because this is a 0, it means it's an x-intercept of negative 4, 0. And then my other 0 is x equal to 1. So that's my other x-intercept, which is 1, 0. I can also tell by looking at the fact that this has odd multiplicity that each one of these zeros is going to cross at the x-axis. So I want to make sure I'm making note of that and I'm writing that down because that's going to help me when I'm sketching a graph of this function. So this has odd multiplicity for each of these zeros. So that means it's going to cross the x-axis. All right, I'm going to erase some of this stuff so I can make up more space here for me to write. Now, what about finding the y-intercept? To find the y-intercept, I'm going to have to substitute 0 for x and solve for the y. So I'm going to basically be finding f of 0 Every time I see an x in the polynomial function, we are going to substitute 0. Let's go ahead and do that and see what we get. We're going to get negative 1/2 times 4 times negative 1 raised to the third power. When you raise negative 1 to the third power, you're just going to get negative 1. And when you multiply all of this out, we're going to end up here with a positive 1/2 times 4, which is 4/2, which simplifies to 2. That means our y-intercept is going to be 0, 2. So we have found our intercepts. So we've basically done step 1, step 2, step 3 in all of this. Step 4 says determine the maximum number of turning points on the graph of the function. Because the degree is 4, that's going to help me in finding the turning points. The formula for turning points is n minus 1, where n is the degree of the polynomial. So this would be 4 minus 1, which is 3. So this would represent the maximum number of turning points that I could possibly have on this polynomial function, right? It doesn't have to have 3 turning points, but this just represents the maximum number that it could have. So I just want to make sure I emphasize that it doesn't have to have 3, but it's the most that it could have if I were to look for turning points. Okay, so we have done that. And let me go ahead and start drawing the graph and start labeling some of these important points. I'm going to go ahead and choose some values that are in between my x-intercepts. So this is kind of like my step 5, where I find additional points on the graph on each side of any x-intercept, just to help me sketch this graph. So maybe some good values for me to choose in this case would be maybe like -5, -2, +2. So these are just some values that I'm using here to help me sketch this graph. All right, so in order to find these ordered pairs, I'm going to have to substitute the values that I chose here for x. So if I plug in -5 for x, I get f of -5 is going to be equal to, this is going to come out to -1/2 times -1 times -6 raised to the third. I can tell right away this -6 raised to the third is going to give me a big number. So at this point, you might want to even stop and not worry about this one particular point here, because you can tell that this basically is going to go down towards -infinity, the smaller that x gets, the value of x. So that might be something that you might take note of right here. As soon as you see you're going to get a very large value, this is not going to fit on my graph. You might just say, I'm just going to draw my graph going down towards -infinity with an arrow here on this side, on the left-hand side of -4. I'm going to write this value down just so that you guys can see that. Okay, now we're going to substitute that -2. Before I substitute -2, let me just move some things around here so that I have more space to write this problem. I'm going to move this up here. And now I have some more space. Let's find f of -2. So f of -2, every time I see an x, I'm going to substitute -2. So it's going to be -1/2 times -2 plus 4 times -2 minus 1 raised to the third. This is going to give me -1/2 times 2 times -3 to the third. -1/2 and 2, I can already tell that those two values right there are going to give me just a 1. And then it's a negative times a negative, so it's going to be a positive. So my answer is just going to be 27 here. Now that is kind of a high value, but you know what? I'm going to just kind of extend my y-axis a little bit here, and we're just going to kind of like estimate it and just kind of say, you know what? Let's just pretend 27 is right here. And, you know, this isn't necessarily the maximum value. You know, it could go higher than this point, but this is a pretty high point for me already. So, and this is just a sketch. So, but this to me on my sketch, it's gonna look like it's the highest point, but it might go higher than this. I would have to probably check out my graphing calculator, but I'm teaching you how to do this sketch without your graphing calculator, right? So the whole point of this sketching polynomial functions is to learn how to graph these without relying solely on a graphing calculator. I've mentioned this in my class many times where it's not good to just rely on the graphing calculator all the time. It's good to know how to do things without the graphing calculator too, right? All right, so let's go ahead and find f of 2. So if I plug in f of 2, I'm going to get -1/2 times 6 times 1 to the 3rd power. So this is going to give me -3 times 1, which is just -3. So I could definitely fit that value on my graph. Okay, so now we've got all these points here. I think we have enough points here to go ahead and sketch this. We know it's going to look something like this, or it's going to open downwards on both sides. We didn't know what was happening in between, but we know now it's going here, like all the way up to like this 27 for the y, and it might go higher than that 27, but it's just a sketch, which is just helping us draw a sketch here. It looks like they're going to look something like this. And of course, we can check this graph by using your graphing calculator. I mean, we've got the graphing calculator. It's good to use, but it's also good to know how to sketch these polynomial functions without relying solely on the graphing calculator, right? So it's good to know how to do that too. So we're learning how to do that. So it's a good idea to use the graphing calculator to check your work, right? So here, notice that this one only had one turning point, even though when we did our little formula, right, it had said there is a maximum of 3 or at most 3 turning points. But this particular problem, or this particular graph, only had one turning point. So please recognize that just because we use that little formula that we had from 5.1, that number does not necessarily mean that you have to have that number of turning points. It tells you the maximum number that you could have. All right, number 2. Before I start off number 2, I'm going to go ahead and just use this y-intercept that's given to me right away right here. And then I'm going to do a little bit of factoring by grouping in order for me to be able to find the x-intercepts, or the zeros. And also, not just the zeros, but I also want to find the multiplicity. So that's why I'm doing the factoring. So doing this factoring, I'm noticing here that there's a common factor of 2. That means because there's a common factor of 2 within one of these factors, there was a common factor of 2 at the very beginning that I just missed. You could have factored out this 2 from the very start. And then I've got the difference of 2 perfect squares, so I can factor this even more. So finally here, I have the factored out version of this polynomial function. Let's make this a little bit smaller so I have a little bit more space. Now that I have all the factors of this polynomial function, I can set each one of these factors equal to 0, and I can find those zeros, or those x-coordinates of the x-intercepts. I can also tell that the multiplicity for each of these is 1. So I know they all have an odd multiplicity. They are all going to cross the x-axis. My first 0 is -5/2. My second one is -1, and my third one is 1. Once again, all of these zeros have a multiplicity of 1. And because that 1 is an odd number, that means that these values of x, or these where these create the x-intercepts, that this function, it crosses the x-axis at each one of these values. I'm going to go ahead and start drawing my graph so I can start plotting these points. I'm a little bit of a perfectionist, so I apologize if I keep drawing these over again. I'm trying to just evenly space these out. Okay, so I kind of tried to space these out as nicely as I could so you could see where my zeros are at right here. This function is going to look like the power function y equal to 4x cubed. And because it's a positive x raised to the odd power, I know it's going to look something like this little graph that I drew here, where it starts off, you know, down and then it goes upward. I don't know what's happening in the middle. But I do know that if I use that little formula, that n minus 1, 3 minus 1 is equal to 2, the max number of turning points is 2. So it could look something like this right here. And that's what I'm guessing it's going to look like because I do have 3x intercepts. I also know that the y-intercept is at negative 10. So I'm going to put a point here at 0, negative 10. Right? So that helps me when I'm sketching my graph. Now it's helpful to have a few extra points. I'd really like to know like f of negative 2. Where's that at? Because that would help me sketch this graph a lot. So I'm going to go ahead and find that one. I'm just going to plug this into the calculator, okay? So I'm not going to show all the steps like I did last time. So if I plug this into the calculator, I get f of negative 2 is equal to, well, I'll show the setup because I'm a nice person. F of negative 2 is going to be equal to 4 times negative 2 cubed plus 10 times negative 2 squared minus 4 times negative 2 minus 10. And then if I put this into the calculator, I'm going to get f of negative 2 is equal to 6. That's a nice value. That'll fit on my graph. Let's go ahead and plot that point. So this is enough for me to sketch this graph right here. So I know exactly where this graph is going to be crossing. It's going to cross here, it's going to go up here, and then it's probably going to go up a little bit higher, and then it's going to come back down, and it's going to come back up, and it's going to look something like this. I'm going to label my points because I've always stressed that to my students, how I always think it's important when you're drawing a graph to label your points so that, you know, everyone knows which points you meant to plot here. And I always like to label the function as well. I know this is kind of a long function, but it just shows that you have confidence in your work and you know what you're doing. So we're going to label our function as well. And notice how I drew arrows, right, where there were supposed to be arrows. All right, so that's our function. There's our sketch. Okay, let's go number 3. Use a graphing utility to graph the polynomial function and choose a suitable window to view all turning points. I'm just going to go ahead and do this one on the graphing calculator, and I'm just going to show you basically how I did it on the graphing calculator. So let's go ahead to our graphing calculator and plot this, or, put this in as a y sub 1 into the graphing calculator and graph it, and let's see what we get. Okay, so here I am on the graphing calculator, and I am plotting. So I'm going to plug this in as a y sub 1 function here. Okay. There, looks like I got the function all there. I can tell by looking at the graph here on the side that I'm not getting all of my turning points showing up on my graph. I'm going to have to adjust this. Let me try doing zoom fit. Sometimes that works. Okay, that did not work. We're going to have to try something else. Zoom fit did not work for us. My graph does not look like that overall. We need a better picture representing the graph. I'm still missing the turning point right here. Let's adjust the window. This is kind of a trial and error process. I'm going to make the y min equal to -5. Let's make the x max equal to, I don't know, let's say 8. I'm going to keep the x scale at 1. Y min, let's go down to -40 and see if that works. And the y max, how about, let's try 150. Oh, I accidentally put in 15. I messed up. Okay, so that's obviously not going to show me the top of my graph. Let's fix, I meant 150. Almost. Let's go a little bit higher than 150. How about 175? Gosh, I just can't get it. This has to work. Let's try 225. Yes, it worked. Finally. Like I said, it's a trial and error process. You know, sometimes just trying to figure out what's the right window that's going to work for you. Trying to make just a nice, like, educated guess right here. All right, so I can see my graph. I can see my turning points. I can see I've got there several x-intercepts. And if I go here to my table values, here's -2, 0, 0, 0, 2, 0, and 5, 0. Oh, my x-intercepts show up nicely on my table of values. I didn't even have to calculate the zeros. So those were all like nice integer values there. Wow, we lucked out, huh? The turning points, if for some reason you really wanted to get these turning points, you can by calculating the minimum and the maximums. And that graphing calculator will do that for you. And I'll show you how to do that. Before I do that, why don't I go ahead and copy that picture, that graph overall, and I can paste it on my notes here so it's available here on my notes. So I'm going to go ahead and do that. Let me just go ahead and find my snipping tool. This might take me a while. Oh, or maybe not. It's right there. Let's go we're going to copy and paste. And there is my graph. So that way I can see what my graph looked like. And why don't I also copy and paste the table of values here, because this was a nice table of values because it gave me all of my x-intercepts. And these are sometimes important values that we need. So I'm just going to go ahead and copy and paste this table of values so that I can refer to it if I need to, and put it on my notes. So it makes it easy for me to identify those x-intercepts, even though they look like you could tell what they are by looking at the graph. But sometimes, you know, based off on approximations, you can't really be sure. And now I can be 100% sure by looking at the table of values. Now, what I'm going to do is I want to also calculate the minimums and the maximums here. So I want to find basically the turning points. Right? I know it didn't ask for this on the problem, but I'm going to calculate the minimum. I'm going to calculate the one that's most on the left, get the left bound first, and then we got to go on the right of it, right bound, and then guess, press enter, and that gives you the minimum value. You see? Y is equal to -25.7. So I'm going to go ahead and copy and paste that as well, because sometimes these are important values that you might need to know, and you might need to be able to find these. So I'm just going to put that and paste it on my notes as well. And it didn't ask for this, but I think it's important that you guys know how to find these values in case you are trying to draw a sketch of it and you're like, I wonder what that smallest value is there for y. And I'm also going to get this other relative minimum that's on this side. So I'm going to calculate the minimum again. Left bound, right bound, and then guess. Looks like this one is y is equal to -14.48711. I'm going to copy and paste that and put it on my notes. That way it reminds you guys of how to find these values. And, let's go ahead and fix that and put this right over here. There we go. And last but not least, let's find that relative maximum. That's over here. So that's number 4 we're going to click on when you calculate for the maximum. Left bound, right bound, and then hit return or enter on guess. And it looks like that highest point for y is 193.8. That's the one I was really struggling on fitting it in the window. So let's go ahead and copy and paste it. And like I said, it's nice to know how to come up with these values, because these could play important values, especially when you're trying to draw a sketch of this graph and you want to know how high does this function go. You want to make sure your sketch sometimes is a little more accurate. All right, so I think that's it for this problem. All right, good job.